Hey there, chemists. In this lesson, we're going to look at solubility equilibria. In our previous lessons, we were talking about complex ions and how highly soluble they are. We're actually going to switch gears here and talk about things that are fairly insoluble, and specifically look at things that ionize to some extent. So, for example, recall from semester one, the solubility rules. Well, those weren't really the entire picture. Some things that we think are very insoluble are really just sparingly soluble, such as calcium fluoride. Unlike other halides, most fluorides are very insoluble. So if I wrote the formula CaF2 for calcium fluoride, we would go, that's an insoluble compound. But the truth is, a small amount of it does dissociate into ions. And you would write it the same way you would write the dissociation of any ionic compound, in this case, 1 calcium and 2 fluorides. It's very sparingly soluble, so we usually use a pair of reversible equilibrium arrows. Now remember, when we write something as an ion, it's implied that it's aqueous, as opposed to a neutral compound, it's implied that it's its standard state, in this case, a solid ionic compound. And these dissociations have equilibria constants. These are called solubility product equilibria constants, and we just abbreviate it as KSP. Because it's only aqueous ions on the right-hand side, we can simply write the concentration of each ion raised to their coefficient, so the fluoride gets squared, but the activity of a solid is 1, so this doesn't include the solid calcium fluoride. It's just the numerator that we normally see in an equilibrium expression. And this is called the solubility product expression. But it's just like any other KSP or K value that we've seen in the past. The thing to note is that they're typically very small. So things that we remember are insoluble for their solubility rules, such as silver chloride, lead iodide, and a few of these others, they have very, very small KSP values. Silver chloride is on the order of 10 to the negative 10. Lead 2 iodide is on the order of 10 to the negative 8. Gypsum or calcium sulfate is on the order of 10 negative 5. Mercuric sulfide is very insoluble, but still has a quantifiable solubility with a value at 10 to the negative 54. So every solid has a unique K value, and just like every other K value, it only changes with temperature. And a small KSP means the solid is very insoluble. That's the point of this. But someone like an environmental chemist, or anyone else, frankly, in the chemistry industry might be very concerned with, even if it's very insoluble, how much do I actually have? So these values give us ways to quantify what amount does go into aqueous solution. So we're going to look at how we use those today. The first problem asks to calculate the numerical value of KSP given what's called a molar solubility. A molarity for these things, that's a solubility expressed as a molarity. And it's proportional to how much of each ion is present. If you think about the dissociation of a compound, in this case we have this bismuth sulfide compound. We're going to write the dissociation. You write it as 1 of the compound, Bi2S3, give it a pair of reversible arrows, and break it up into the respective ions. There would be 2 bismuth ions, and think about the crisscross rule, that must be a bismuth 3 plus cation, plus 3 sulfides, each with a charge of 2 negative. So the expression for the equilibrium constant for this, KSP, would be the bismuth ion squared and the sulfide ion cubed, and we simply write that. So I have bracket Bi3 plus squared, bracket S2 minus cubed. And those are proportional to each other because we just showed that they dissociate in a 2 to 3 ratio based on the formula. And for every 1 of the bismuth sulfides, we get 2 bismuth ions and 3 sulfide ions. And one of them dissolves at a molarity of 10 to the negative 15. So if we have some unknown for the molar solubility, in this case, let's usually call it X, we can abbreviate what the molarity of each ion is proportional to that original compound. There's twice as much of the barium ion as there is of the original compound, and there's 3 times as much of the sulfide as there was of the original compound. So these turn out to be proportional expressions to the original compound, and we still raise them to their coefficients, so square it and cube it. There turns out to be 108x to the 5th. But in this case, we actually know what the value of x is. X is the molar solubility. So if we plug in 1 times 10 to the negative 15, I get 108 times 1.0 times 10 to the negative 15 to the 5th power, which gives us 1.1 times 10 to the negative 73. Very small number, again showing how insoluble these things are. So let's see if we could turn this around. Let's say we have the KSP value of a substance, and we actually want to know what's the molar solubility. In this case, we have an unknown X value. And this tells us how much of the original substance would actually dissolve. In order to do this, I first need to remind myself the formula of the compound is silver chromate is Ag2CrO4, and then I'll write the dissociation that goes with the KSP value. So there's 2 silver ions, 2 times Ag plus, and 1 chromate ion, CrO4 2-. And then setting up sort of an abbreviated Rice chart for every X of this compound, I'm going to make 2x of the silver ion and x of the chromate when it dissolves. So our KSP value, which is given as 9.0 times 10 to the negative 12, is equal to the silver ion concentration squared, which is 2x squared, times the chromate concentration to the first, in this case x. So that means this equals 4x cubed. And we have a very simple cubic to solve, and you get the value of x, which is 0.00013, and that's the molarity. That is the molar solubility. That's the concentration that we could make of silver chromate in a saturated solution. Remember, saturated means it's at its maximum amount. This is how much silver chromate would actually dissolve. And it would turn into twice that of the silver concentration and exactly that of the chromate concentration. Now, what if we don't have pure water, but we have a solution of some other ion? How does that affect the solubility? Well, I'm going to write the same exact dissociation for the original compound, silver chromate, Ag2CrO4, dissociates into 2 silver ions and a chromate ion. And this time we have 0.1 molar silver nitrate. Remember, nitrate is a spectator ion, always. All those soluble ions we learned about are still very soluble, so they don't come into play in this case, although I guess they would affect the solubility of something that has a nitrate ion. But in this case, my molarity of each ion isn't 2x and x. It's going to be however much I have from the silver nitrate compound, which is 0.1 more, plus the 2x I get from the dissociation of the original compound. The chromate value still has an x for its concentration, and it's the same compound, so I still use the same KSP value. 9.0 times 10 to the negative 12 is now equal to the quantity, 0.1 plus 2x, and then square it, times x for the chromate. Now we could expand this and solve a more complicated cubic expression, but look at how small most of these solubilities are. Compared to 0.1 molar, something like 1.3 10 to the negative 4 is insignificant, well below that 5% rule. Just ballparking it and looking at it, we can see that. So the silver ion concentration, let's approximate, as really just 0.1. We're not saying x is 0, we're saying that 2x is negligible compared to 0.1. I'm still going to dissolve some of this silver chromate, but however much silver ion I gain from that compound is insignificant compared to the amount that I get from this 0.1 molar silver nitrate that I'm starting with. So this actually makes it a much easier problem to solve. It's now just linear, and we get X is 9.0 times 10 to the negative 10, and it is a molarity. I know we usually write K values as unitless, but we turn these into molar solubilities. And the point is, this is much less soluble. Much less soluble than the previous problem. And conceptually, that should make sense if you think about an equilibrium. Remember, these are all affected by Le Chatelier's principle. And in this case, we are adding silver ion from the silver nitrate. And a stress to this solubility equilibrium would shift the equilibrium to the left, meaning I have more solid and less of the soluble ions. And indeed, we get a much lower solubility in the end. So this is just Le Chatelier's principle all over again. Let's write that just to remind ourselves for later. Le Chatelier. We use that concept very frequently whenever we talk about anything related to equilibria. So just to wrap up, that's how you can make ions less soluble. How do you make ions more soluble? Well, we can try adding other things to affect the equilibria. So what would happen if we looked at the solubility of each of these three compounds, some highly soluble, some not, but regardless, in the presence of 1 molar hydrobromic acid, or HBr. Remember, this is a strong acid, so this totally dissociates into hydrogen ions and bromide ions. When I see aqueous HBr, that's what I think is really going on. So I have a molar of each of those, and that could affect the solubility of each of these things. First, let's just write the solubility equilibria for each of them. Sodium bromide would dissociate into 1 sodium ion and 1 bromide ion. Magnesium hydroxide would dissociate into magnesium ion and 2 hydroxide ions. And lastly, silver nitrate could dissociate into 1 silver ion and 1 nitrate ion. Now, what does HBr do to this? Well, for the first one, bromide, is a common ion. In other words, it's present in both the original compound, the sodium bromide, and the thing that we're adding. But again, if you think about this as a Le Chatelier's principle question, we're just stressing it by adding bromide. That will shift it to the left. We'll get more NABR solid, and this will be less soluble. Equilibrium shifts left. So this is less soluble. So what I'd like you to do is hit pause and simply look at the last two. How is HBr going to affect that equilibria and that equilibria? Thinking about Le Chatelier's principle each time. Okay, for the second one, we don't have a common ion, but we have hydroxide ion present in the original solution, and that will react with the hydrogen ions from the acid. So this means we're going to shift it to the right. Because if this happens, and that would be just an acid-base reaction, that's the same as removing hydroxide ions. So that would force the equilibrium forward to the right, and then you end up with a more soluble solid. That should also make sense conceptually that a base easily reacts with an acid. In other words, when that reaction happens, you get solubility. And then the last one also doesn't have a common ion, but there's also a reaction at play. The silver ion will react with the bromide. So that will effectively remove silver ion. You will shift it to the right, and you get something that's more soluble. So these are a couple of ways to change the solubility of various solutes using primarily Le Chatelier's principle for this, whether you're comparing the solubility of something that's typically thought of as not very soluble, or even something that is very soluble. Le Chatelier's principle is still at play, and we can quantify all these solubilities by looking at KSP values, which are tabulated for every substance.